retrouver pour la suite du 4e rendez-vous de l'IA ici à l'UTC. Thank you very much to everybody for being here again for the 4th AI RendezVous, which explores the transformative role of artificial intelligence in the fields of human nutrition and health. Et nous sommes désormais en compagnie de Frédéric Delbecq, enseignant-chercheur au laboratoire TIMR, Transformation intégrée de la matière renouvelable de l'UTC-ESCOM, Teacher Researcher of TIMR Laboratory. On va parler de contribution de l'IA dans les activités de recherche de ce laboratoire. Allons-y, nous vous écoutons avec une grande attention, Frédéric Delbecq. Merci à vous. On peut l'applaudir et l'encourager bien fort. Merci à tous. Thank you.
I hope you are hearing me. So, good morning. Today I will introduce you the laboratory TIMR, okay, which is a joint lab between UTC and ESCOM, an engineering school of chemistry located in Compiègne. So today I would like to explain how IA could act, could play in the in the near future in our research work, okay, and of course, in the same time, I would like to explain also what is TIMR. So TIMR is a research laboratory dedicated to the transformation and valorization of biomass and renewable matter. And we have TIMR includes 5 expert teams with different specialties. For example, we have specialists of chemistry, physicochemistry, biology, engineering process, and so on. For example, in my case, because when Audrey asked me to make a short presentation about EA and the possibilities in our research, I didn't want to speak especially about my research, okay? But for example, in my case, I'm working in the field of green chemistry, and I focused on the synthesis of bio-based monomer from the platform molecules, and I want also develop, I'm trying to develop new polymers to become substitute of petroleum-based materials. In the case of TIMR, okay, we have in this moment 3 scientific thematic areas. The first one is we want to make some strategies. We want to develop some strategies to realize the decarbonation of process, and at the same time we want also to develop new materials, bioproducts, to replace, I've told you before, petroleum-based, for example, plastic and so on. And finally, we want also develop new strategies, new technologies to reduce impact on the environment and also impact on the human life. So usually in TIMR, we are working at different scales. So we're starting from chemical interactions. So we are starting from compounds, for example, and then we will try every day to make formulations to get more complicated materials and products. And finally, we are also able to develop process, so in large scale, of course. And usually, when we want to make some kind of prediction of modelization, we are using Cosmos. It's a software, And for example, with this software, we will be able to predict solubilities, CMC, and so on. And usually, so generally, we used QSPR, so quantitative structure properties relationship. So it's traditional method to one more time develop. It's easy, maybe not so easy, but sometimes it's possible to access to dispersibility, GG, etc., etc. But in fact, the main problem is we are always studying simple system. In fact, if you want to study more complicated system, we have to go further. And also, if we want to save time and money, maybe it should be interesting to introduce AI in our research work. So, because we have a lot of field of research, I've made a pickup. So I've chosen some representatives, the most representative field of research we have in our group. So as you can see here, I will speak about, for example, natural products extraction with supercritical carbon dioxide. And as another example, for me, I am currently using deep eutectic solvents for making organic reaction and oligomer production. So deep eutectic solvent is also another type of, it's a new type of solvent currently used in your laboratory, also for extract natural products like protein. Just after, I would like to speak about methane production. Some researchers from our team are currently develop strategies to produce methane from anaerobic digestion of biomass. And I have another colleague sitting in this room here who is currently studying pyrolysis of biomass for producing many kind of material I will speak about later. So, of course, for some other people are working on the study of small compounds. They study CMC, so the critical micelle concentration for surfactant. And in my case, I'm studying usually also gelation of small compounds in many kind of liquids, like organic liquings, water, and so on. So, in my opinion, AI could also help us for predict reactivity of chemical transformation. So I found, as you can see here, I found a reference, a recent one, about 5-HMF, so 5-hydroxymethylfurfural oxidation or reduction. And it should be interesting to develop, maybe, in my opinion also, one more time, some model to predict this kind of transformation. And of course, because I've told you, I'm working on polymer and monomer, so I think if someone could help us to complete my work for preparing model to predict monomer reactivity or to predict also the physical properties of polymer, it should be crucial for us. Okay. So, because, I'm sorry. I return. Okay. Because bon, for this presentation, in fact, I looked for many examples of papers, of articles, the most recent, describing similar research using AI. Okay, and for the first one, for natural product extraction with carbon, supercritical carbon dioxide, they used many I'm sorry. I forgot the word. They use pressure, temperature, and pH to make simulation of the extraction. And then, usually, because I've told you I'm not a specialist, of course. So I report here in the middle of the slide the normal process to make simulation. So we need, of course, a lot of experimental data. Also, we need to collect data from the literature. We have to select a model, make a train, and finally, we have to announce the system, the program. And for this purpose, as wrote here, okay, recently there is, because I've told you I'm a chemist, okay, there is some library, this is some program and language called SMILES that could convert the chemical structure into on va dire something easy to understand for the system, for the program. Okay, and of course, recently, because I tried myself in my home with my computer, I discovered RendezVous. Okay, RendezVous is a library available on internet, easily download, easily accessible, and I was able to make some simulation. Okay, and to finish for this slide, okay, on the right, okay, I wrote, I found 5 recent papers about. I'm so sorry. My work about these research results. Okay. So because before I was speaking about natural product extraction with carbon dioxide, I forgot to speak, of course, about DES, because DES is complicated mixture of 2 compounds, okay, and these compounds could be also described using SMILES, and in both graphic, they were able to prove, to predict the results. The first one is using linear regression type graphic. They will be able to predict the natural product extraction, and in the second one, they were able to predict the CO2 capture, donc ce CO2 capture, carbon dioxide capture, using different type of DES according related to the nature of the elements used in the DES. Okay. I'm sorry, I'm just So in the next slide, they realized, so some researchers realized a simulation about a complete process for methane production. And one more time, they used a model, and finally, they were able to produce a linear regression to validate their work. In the second work of this slide, another team of researchers were able to predict the different byproducts and products of the pyrolysis of biomass using also another type of machine learning. Of course, as you can see here, I found two other recent references. Okay. So, I'm sorry for what I told you before. Now I will speak about the current work of your laboratory. So I've already checked if we have or not papers or articles about research containing machine learning or simulation. So I found only 3, and 2 of them are mine. The first one on the left is about the study by DFT, so density functional theory. So I've told you, it's about the prediction of anti-corrosive behavior of coating made of benzoxazine monomer. The second one, in the middle of the slide, is about the machine learning predicting the gelation ability of surfactant type low molecular weight gelator in many kind of liquids and solvents. And the last one is not mine, of course. It's another paper about simulation of solubilities of new compounds by means of DFT using a COSMO-RS program. Okay, so they made combination between both of them. So about CMC and evaluation of surfactant capacities, surfactant properties. I reported here also 4 recent papers, articles found in the literature. And the first one on the left side in the upper part of this slide, it's about one more time the using of COSMO-RS by introducing on-cell parameters, okay? And in the second one, just under, this is another paper, this is another work, where researchers were able to predict the size of particles in a dispersion of oil in water in presence of a surfactant called T20. So as you can see here, the dot line is the dot line were all predicted line, and the plenty line, I don't know if it's possible to say that, it's the real one. It's from experimental. As you can see here, this is completely compatible. In the bottom of the slide, you can find also a table. I'm sorry, it's difficult to see, maybe, I don't know, where they were able also to predict the properties of surfactant. And finally, here on the right side from GCIS, Journal of Colloid Interface Science, this is a recent article of 2022. They use also, for the first time, I show you what is SMILE. Okay, I'm so sorry, because SMILE, as you can see here, this is just a representation of, in a line, it's just it's a writing, okay? And this kind of encoding, it's easy to be treated by the computer. And then, as you can see here, we have whole steps useful to predict the CMC, for example, of a surfactant, because this is a surfactant, this is SDS, sodium dodecyl sulfate. As I've told you, now I'm working on bio-based monomer synthesis, and I wrote before in the other slide, it should be interesting to predict by machine learning, the reactivities of monomer, especially without metal, so with polymerization catalyzed by just an organic catalyst. And as you can see here, this is a non-published results, because I worked with a young guest researcher, and I asked him to produce some DFT. So I've told you this is a density functional theory, specific program useful to predict the energy level of small compounds and polymer also. And in the near future, it should be interesting. Because I saw some examples in the literature. DFT is full compatible with machine learning, so maybe if someone somewhere wants to continue this work with me, I would like to develop this kind of work. And later, so I showed you another work. So this is another article found in the journal Polymer. They described or reported, they have reported a study about the copolymerization of two monomers. And from now, it's easy to predict the reactivity of two monomers in the same batch. And R1 and R2 are the characteristic values called reactivity ratio, usually found to predict or develop a new material like a copolymer. And finally, so I've told you, for small compounds, it's possible to use SMILES. This is a language, okay? And recently, for the polymer, because I'm working on polymer, some researchers have developed a new language called Big SMILES. And in this language, okay, we are just working with small sequence of the polymer. And of course, this sequence is in relation with many kind of properties, okay? And on the slide, on the middle of the slide, I show you a script available on the website of a paper, okay? And they have already downloaded Big SMILES and RDKit to work, okay, to predict the properties. Here it was the TG, so the glass transition temperature of a polymer. And if we check the results, it's clearly near to the reality. Okay, because as I told usually to the students, for example, for a molecular weight of a polymer, you have a specific value of TG, and they were able to predict the results. So to finish with these slides, as you can see here, there is also 6 recent articles about the subject, and I would like to participate in the near future, if possible. So, so to finish my presentation, so I hope I was able to convince you to work with us. Okay, so of course. I've told you today I was not here to make a presentation about my work, so sometimes it's complicated for me to explain everything because I have a lot of ideas. But maybe we have many fields of research, so it should be interesting for everyone in my team. I'm sure to inject AI in their work to go further to face off the demands of the real world. Well, thank you for your attention. So,
Thank you very much. Merci.
if you have any question.
Oui, on va voir s'il y a des questions. Y en a-t-il? Do you have any questions in the room? Or yes, I'll come to you with the microphone.
I hope I could answer.
Merci.
Maybe
Présentez-vous.
Hi, so Yves Grandvalet, I'm at EDIASIC Lab, and I was wondering, so in most work I know about macromolecules, they are mostly about proteins and living matters, and I was wondering to what respect these studies are relevant for the representation of molecules such as polymers.
Okay. So first, I would like to ask you a question. You are thinking I am working about protein? No, not really.
So I understand maybe wrongly that polymers are macromolecules,
yes,
and macromolecules that have been really used a lot in with AI are the types of proteins and
yes. It's not.
I was wondering if you could use, you could leverage this type of studies for your own benefit.
Okay. What I want to develop in this moment is just, for example, you know, I'm trying to develop simple polymer, so just like polyester and polyamide. And what I want is just to predict the properties compared to the well-known polymer, petroleum-based polymer. I don't know if I. So you. I have another question for you. Just you want to know if I want to predict the structure, the 3D structure? No, not really. No. What?
I was so a molecule is not so typically the easy things in machine learning is to deal with vectors.
Yes. Vector. I know.
Molecules are not vectors.
Yes, okay.
So you need a way to transform these molecules into vectors, and for this, there's been
a
lot of works in proteins.
Like this.
And I was wondering if you could use the same kind of tricks, or if you need to go towards specific pipelines.
I understand what you mean. Okay. So this is the reason why now I'm looking for someone able to help me to go further, because as you can see here, what I am able to do, for example, I can convert and make many things with Morgan fingerprints. It's obtained from a vector like this. Okay, it's a 2D representation of a small compounds. And as here, I found this article is very interesting because they are using, I've told you, big smiles, and it's quite different from smiles. They said that. But for the moment, I have no time to study that thing by myself. But if I can't find this time, I will be happy to do the same thing with my polymer, because in this paper, in this article, maybe it was the first one, I think. In fact, they have only developed a method to predict the properties of well-known polymer, commercial one, the petrol-based. I don't know if I...
Okay, maybe we will talk together after.
Yeah, okay.
Thank you. Another question for you, a last question.
Okay, so, okay, if I understood what you say, petroleum polymer are well studied, and thanks for the talk, by the way. And you want to study other kinds, maybe nature-based polymer.
Yeah.
One question I had, so in the talk you focused mainly on predictive power, so of trying to make a surrogate model or learning model that could predict things. I was wondering if in the fields of polymer and so on, and in the lab, people also wanted to take a peek inside the black box. So black box
yes,
name was mentioned before.
Yes, I know.
And if you're also interested in explaining or entering into the so are you interested in knowledge discovery as well, and in this case, which case of knowledge beyond mere predictive power? That was a question I had.
Thank you, Sébastien Delbecq.
Okay. Two? I have to answer.
Yes.
Yes. Yes, I guess there is a black box because I need to make a lot of experiments because there are new or novel materials. So I wonder, I guess it should be maybe too early. I'm not sure. But if I do that thing, it should be wonderful, I think. Yes, but there is. If you want to speak with me later, if you have any idea to work on, I'm so happy. I'm so sorry because I have no more answer to your question.
No,
I'm
it's
so
okay.
sorry. But
Thank you.
I have many ideas, in fact, but it's complicated for me to speak in front of a lot of people,
Yes.
especially in English, because I'm better in French, I think.
You're good in English too. Thank you very much. We can applaud, please. Frédéric Delbecq. It was very interesting too. Thank you. Thank you very much. Let's introduce now, please, Nathan Masera, business developer for Big Chemistry. Please welcome Nathan Masera. He holds an engineering degree from ESCOM with a specialization in formulated products engineering at UTC. His activities span to go to market engineering, technology watch in AI and blockchain, and equally technical content creation and training. Its subject now for you is how transforming the art of formulation into a data-driven science with Big Chemistry. We listen to you.
Bonjour. Hello, everyone. So yes, I'm from the dark side. So I was trained at UTC and ESCOM, and be assured, Professor Delbecq was one of the best there, even if his English is not that good, but he's the best. I'm very happy to be here, seeing friendly faces. So I'm here to present Big Chemistry. So, and we're going to talk about self-driving labs, which are kind of autonomous laboratory. So this is where we get AI in it. So I'm from the cosmetic industry. So, but my knowledge is in every chemical industry. And I wanted to tell you that this industry is really in transition. Why? Because the first forces is consumer. So my generation is changing their way, and we are changing our way to consume. The generation above, the new generation, is doing the same thing even more. So when you look at the numbers, for instance, in cosmetic, over half new beauty and personal care launches carries ethical and/or environmental claims. The same for all the industry, detergent, coating, etc. The second forces is the regulatory pressure, especially in EU. We have the PFAS, we have the macroplastics, and lots of other regulation that also can apply to changing formulation. For instance, the supply chain. If you cannot have a good supply chain, you will need to reformulate too. So both forces will make our industry change the product, and we need to reformulate them. And when you look at the number, just the PFAS restriction, it's more than 10,000 products to change. So how can we do that fast and at scale? Because we have a reformulation problem. Why? Because today it's slow and expensive. If you want to change a petroleum ingredient, you cannot do one with a new bio-based ingredient. It's impossible, because you will have to, it's a all new chemistry. So you will have to change stability, texture, even efficacy, not just in cosmetic, but coating. The whole industry is impacted. There is a study, we think that between 35 to 65% of the PFAS affected products are reformulable. So all the others, there is no solution known today. How can we do that? And in theory, DO exists, but so I was told at ESCOM to do, in French we say plan d'expérience. I was told to do that, but in fact, in most companies, you don't have the resources to do it. So we need another way of doing it. Other thing is that most experiment that we do goes nowhere. So there is a study by Enkel. I know it's a small study on a small part of the portfolio, but they say that the normal way of doing formulation, the try and error, it's only 8% success rate. There is also, I saw it this morning in Infochimie, Arkema say it's 1 in 15 formulation that goes that is successful. Something also very interesting is that knowledge is locked in people's mind, especially the senior. This is something to keep in mind. And if you want to change formulation, you need to understand better your formulation. You need to explore your formulation space. When I say formulation space, that when you have a formulation with 10 ingredients and you have 10 parameters to follow, that's 10 billion possibilities. So how can you explore this space? Because trial and error doesn't scale, and we need a different approach. So I'm here to talk to you about one of this approach, which is self-driving labs. In literature, you will see SDL most of the time. So self-driving labs, you see it on the right, the beautiful picture from the lab at Big Chemistry, and Big Chemistry is working on developing those self-driving labs. They automate the preparation, the testing, the analysis of ingredient and formulation. So it's a closed loop. So first the robot starts to formulate, then it will measure what you are looking for. So for instance, surface tension, viscosity, phase behavior, and then you will analyze it. And so you'll have an algorithm. That's where AI is. It's mostly Bayesian optimization. And when you analyze it, it's not just analyze it, but after every run you make with the robot, you will put data in it, and it will learn from the experiment you're doing and adapt and decide which experiment you're going to do next. So you're seeing a robot doing everything, like, Nathan, like, where's the human? But the human, you need human. It will set the objective, interpret the result. So humans won't go away. You need them. And SDL will be there just to augment the researcher. It won't replace it. So what are the advantages of self-driving labs? I will say SDL now because it's too long. First, it's faster. So when you look at the literature, it obviously depends on the self-driving lab you're looking at, but most of the time you'd have at least 6 times acceleration. And the acceleration factor will increase with the numbers of parameters. So if you have a formulation of just 2 ingredients, which doesn't exist, but you don't have to do and use self-driving labs. But when you have a formulation with 10, 20 ingredients, this is where it's interesting to use. I will say smarter, not to say that our formulator, I'm a formulator, so I won't say that I'm not smart, but you can explore more the formulation space. So the analogy that I have is that when you imagine your formulator without this technology, you need to cross the sea between France and Brittany at night swimming. But with self-driving lab, you're during the day with a boat and a GPS. Something very interesting also with self-driving labs that you can generate lots of data. So I'm not sure if you know high throughput technology, so robotic technology. This is used in self-driving labs to create lots of data and quality data since it's done by the robot. When we're talking about AI, data, it's the heart of it. So you need quality data. And when you do formulation, Jean-Luc will formulate with the same protocol, it will formulate something, and Anne-Catherine will do the same, but obviously it won't be the exact same formulation, even if the protocol is the same. But with the robot, that's a bit different. And again, the more complex the formulation, the greater the advantage. Built by giant, needed by all. So I just put it some major player in the industry doing self-driving labs today, mostly in the paint and coating industry. So for instance, Covestro, Evonik, Henkel. Since we're in Compiègne, there's also Bostik working a lot on those experiments. But this is a problem because we have a structural gap. A full self-driving labs is more than $1 million. Those technologies are accessible now because the cost of robotic decreased a lot. Robotic arm is less than $10,000 today, compared to at least 10 times more a few years ago. But European industry, it's more than 97% SMEs, small and medium entities. So the problem is they don't have the resource to use those self-driving labs. And when you look at the capability of those self-driving labs, it's going to be a really huge competitive advantage. Another problem is that commercial platforms today are all North American. And when you discuss with companies in Europe, we don't really want our data to go to North America. So the question is, how do European SMEs access this technology? And obviously, I'm here to present the solution. My presentation is well done. Big Chemistry. So Big Chemistry is a national funded Dutch research program. They are the best in terms of SDL. They publish a lot, so you have lots of things to read back home if you want. There is 65 researchers today working on the project, more than 10 publications. I think it's in the last 2 years. We have 6 self-driving labs running and way more to come. and 25 active projects within the industry. And of course, we are European. When you look at the competitors, not a lot of people are doing hardware and software. So we are really at a good point. And since we are at UTC, I wanted to tell you a short personal stories. So when I did my master degree here, I was working with a big supplier, a big supplier of silicon, and I was supposed to characterize the silicon film forming properties in cosmetic products. First thing that is funny, what happened to all those silicon that I studied for 6 months? They will all disappear because of the regulation, PFAS restriction, microplastic concern. So all of those ingredients that I worked really hard on, company are going to replace them. But I'm glad they do because it's silicon bad for the environment. Back in the day, I was doing contact angle, wettability measurement, and it took me 6 months to do all those experiments for multiple reasons, but lots of time. It was very slow, manual, and impossible to scale. Why I'm saying that? It's because the first time I went to big chemistry in the Netherlands, they show me this self-driving labs. And this is the exact same thing that I was doing. So I tell the story of my work with the guys who make the self-driving labs. And he laughed at me. He said, 6 months, huh? I could have done it in maybe 2 days. So I was kind of shocked because I did the experiment, and this is live. This is working. I don't know if the image is good enough to show you that this is a real disruptive technology. So yes, it's still in the lab, but even in the lab, this is already something that you could use in the industry. And what you can see, it's a robot doing an automated pendant drop test, which is a very classic test to measure surface tension. 2 other examples that I wanted to show you about big chemistry. The first one is an automated phase diagram. If I have time, I will show you. I have a figure from the publication in Nature. But the first pendant drop test was to tell you can do things faster, like from months to just few days. The automated phase diagram is to tell you that you can be smarter, you can navigate and understand way better your formulation and use fewer measurements. So you will only have, thanks to AI, you won't have to do just few experiments to know your phase diagram. So the study said that you have 80% fewer measurements to do versus a classical way of doing it. The second example I wanted to show you, it's the SurfPro database. So you know AI, it's nothing without data. So if you want to create good model, you need data without bias, you need lots of data. And this is one of the goals of big chemistry, is to create database, structured data to understand the basic of formulation. And they started with this database, which is a database of surfactant. And I don't know if I will have time to explain, but they use an agent to scrap data from publication and then graph neural network to be able to predict properties and the pendant drop test to validate those properties. Very interesting. If you want, all of this are available online, and it's open source on GitHub too. One thing also that I wanted to add is the model doesn't just predict, it tells you how confident it is. So we are mainly doing Bayesian optimization. This is like the standard. And it's different from the AI you hear every day now. you will find value, but also uncertainty in those value. So like this, you can really work scientifically. Yes. And to conclude, so I think we are all pretty sure about that. Formulation is becoming a data science. And I'm here to tell UTC, let's train our chemists to be data scientists, or at least have notion of data science, because the future of formulation is working with those tools. And since it's such a disruptive technology that we'll have to use them if we want to be able to change all the formulation that we need to change in the industry. We'll have to use all the technology available, and AI, lab digitalization, SDL are the tool that we need to use. And this is going to the next point. The bottleneck is not the technology, it's talent. It's really hard to find people that understand chemistry, robotic, machine learning, and also being engineer and orchestrate all of that together to be able to create those tools, or at least understand them to use them properly. And one thing that so last year, this week, I was at Eurocoat, a big exhibition in Paris for the coating industry. And something that's coming back at every booth and every people that I discussed with is regulation. People don't have any clue on how to reformulate their product, and they need tools. So maybe 1 year ago, it was difficult to talk to them, but today they understand that they need something. They need tools to help them. So the regulatory pressure will be a catalyst for the industrial adoption. And as I say, just the PFAS restriction alone, it's like thousands of formulation to rework. I don't know, I am in time. Perfect.
Do you want to go further with some questions for Nathan? It was very interesting too. Thank you very much. So you are a business developer for big chemistry. Are you inspired by what he said just now? Can you show the slide, the precedent slide? Formulation is becoming a data science. It's great punchline, I thought. What do you think about this talk? Do you want to continue? So it's okay, great.
If I have time, I can.
Yes, you have.
Yes.
Yes.
So this is a figure from one of the publication that the second one, the one in Nature, the automated phase diagram. I think it shows well how the self-driving labs work. So here you have 3 steps. One is hidden. So first you formulate. So on this one you have 2 polypeptides that are just mixed together. And then you'll have the analysis part, the measurement part. So you can use whatever you want. Today we can use foaming. I show you surface tension. Here it's particle size detection, and of course the phase separation detection. So this is the measurement part. And then you have the active machine learning. So that, can I see? No, I can't. But the part below. And what's happening is that the model see what are the results of your measurement, and then it will predict what the phase diagram looks like, but with uncertainty. So the different color are represent how confident we are with the value. And the model by itself will know, because the goal of this self-driving lab is to enhance and find the phase diagram. So it will know which point to do next to be able to constitute the phase diagram properly with the less uncertainty possible. And it will go on and on until you reach your goal. I hope it's clear enough. But if you have any question, there's a QR code to my LinkedIn profile. Please send me a question, connect with me. I will be happy to discuss more. And here are the 3 publications from the big chemistry team.
Okay, thank you. It's very clear. It's okay
Thank
for you?
you.
Fine, thank you for him. Merci, Nathan. Let's invite now Giovanni Palma, please. You can come at the office. You are head of AI and computer vision. We are going to L'Oréal now to know much more about AI applied to formulation at L'Oréal. The example in an enterprise, in a society like L'Oréal. Giovanni Palma, he leads a specialized team dedicated to applying deep learning and advanced computational methods to cosmetic formulation and augmented beauty. We listen to you now.
Thank you for the introduction. So I'm Giovanni Palma, as it has been said. I'm part of the Research and Innovation Center in L'Oréal, and especially in the digital transformation. And today I'm going to talk about how we do apply AI for the sake of formulation. And instead of going too technically in the details, I'll try to give you at a glance what are the different types of AI we can use and what are the pros and cons of each of those methods. So before entering the details, formulation and reformulation, it's all about creation of cosmetics, in our case, which actually involve many steps from the actual understanding of the needs, of the user needs, so the consumer, basically, up to considering and scouting any molecules and actives that may have some properties, some capability to do something on the person using the cosmetic in the end. Then you have the formulation, which is rather like cooking, where you put a whole bunch of raw materials together to get the actual formula that may eventually be delivered to the consumer. And before getting actually to the consumer, you need to do some testing so that you can actually assess what's the performance of the formulation, of the formula, and up to valorizing those claims, through some claims actually, to be able to sell that in the end. So today I'm going to focus only on the formulation part. Obviously, AI can actually be involved in all the stages I mentioned before, but for the sake of the conciseness of this talk, I'm going to be speaking a bit about formulation only. So as it had been said previously, so thanks Nathan for the nice introduction. It helps me a lot with what I'll be saying here. Formulation is kind of in constant motion. So you have that problem of reformulation. So you have known formula with known performance, and you want to actually replace for whatever reason. You want to go greener, you want to remove things that are not allowed anymore, and get kind of the same type of formula. You also want to consider new actives and create new performing formula. And in the end, you actually get a continuous motion of creation of formula, and especially as you scale with the number of brands like we have in our case in L'Oréal. Then, as it has been mentioned, to actually be able to reformulate or formulate new formula, you need to characterize so that you know what you're actually creating and what are the good side and bad side of candidates in terms of formulation. And last thing, but not the least, if you are actually at a big scale, meaning that you have not an only one R&D center generating your formula, you may actually want to benefit from what is being done in all the centers. So just taking that example, if you want one center in China, one center in North America, it would be a pity actually to have the both team recreating the same type of formula over and over, while they can actually benefit from what they are doing from each other. So to make a long story short, reformulation actually leads to two technical challenges, which is if I have a candidate theoretical formula, what would be its properties? And if I want to actually shoot for some properties, what would be actually the formulae that may match those properties? So that's where algorithm actually enter the place. And to make it more simple, when we talk about algorithm, AI, I mean, name it the way you want. That doesn't really matter. What is key is it's always a way to model the knowledge to actually achieve some goal. So to start with, we can actually list all the type of knowledge. One type of knowledge is the actual chemistry and matter interaction. So that actually nicely fit with the first type of algorithm, which would be simulation-based. Okay. Then once you don't know actually the law of physics, or they are too complex, or either to implement or to define, you may actually go to another type of knowledge, which is, as we mentioned before, the data, which would be simple, either the formula itself or the characterization of the formula that may actually allow you to enter the world of machine learning and AI to actually train by example those algorithms. Then you have a third part of knowledge, which is the know-how, the expertise, the gut feeling of the formulator, the documents, which mainly be more in the form of writings in documents, for instance, and that's where large language model actually enter the game and do a really nice job. Now they actually being versatile by design. They can actually help you to deal with the data, but also the formula themselves. And as we'll see a bit later, they may actually fall short on being really precise to the characterization part. And that's where we actually may envision the last part, which is the creation of dedicated cosmetics formulation model. And I will give you an example right after. So let's go through those four elements and start with the simulation one. So here I'm going to take some examples, which are overly simplistic, but are meant actually to help you capture the sense of the limitation and the bad side, the bright side of those methods. So let's take that example of light behavior. So light behavior, if I want to make it simple, you can have many type of interaction when the light, the photons actually hit some surface. For instance, like refraction, you have a mirror-like surface or glossy cosmetics. In our case, you may have the diffuse rendering of the light, so kind of scattering. Photon goes everywhere in each and every direction. You have the absorption, so photons actually get absorbed by the surface. Sometimes they actually go through the surface, which kind of inhibit any reflectance. And then you have the change of the color by the filtering of the wavelengths. So those elements, they are kind of easy to quote, between quotes, easy to model because we know them for some times now, and we can actually implement them directly into some computer. However, that actually may lead to complexity, especially when we want to get some accuracy, because here the physics, as you know, the beamer going on the screen, instantly make all those types of interaction massively be treated. When you actually want to model them into some computer, you actually need to have massive resource computation if you want to get something that is decently physically meaningful. So in practice, what you usually end up doing is either simplifying your model or get to wait too long, and you have to make a trade-off. And then there is one thing that I didn't mention, which is while it's kind of easy to actually model the physics interaction, the complexity actually becomes in what we interact with. So here, I just talk about the photons, not actually what is being hit by those photons. So if I take that simple example of some smooth surface where I deposit some coating, which is of a uniform and uniformly thick and uniform materials, then it gets easy to actually simplify the simulation. Now, if I want to simulate the same coating on my lips, which are not that smooth, with some type of wrinkles, heels, and those kind of stuff, and adding something that is not uniform. So basically, I'm doing cosmetics, so I want something that is shiny with pigment that reflects the light in many directions. Then I do not have that hypothesis, assumption of homogeneity, and therefore to get something that is realistic, I need to complexify my system to get something that is meaningful. That's why we usually reserve those kind of techniques for really tiny, simple piece of experiment, because at large scale, so at the full physical scene, it's easy to get something that is realistic, but not really at the level of what we're interested in. Last thing on those elements, it's really easy to actually model the law of physics because they are mathematically written. Now it's way more complicated to actually describe the know-how of the expert, the gut feeling, as I was saying before, because this is not actually math written, basically. So to actually go a bit beyond, what we can do is actually move into the world of machine learning. So in machine learning, the assumption is the following. You have data, and that data actually contain information. So all the rules I was mentioning that are your prior knowledge from before, here they're actually hidden in the data. So provided that you have enough data, and here we are taking an example again on the light interaction, which is again is a fake one, but for the sake of the illustration, let's say you have a formula really basic with two raw materials, and then you have the ability to measure its opacity for various concentrations. So basically you have a bunch of formula, they're all different because they all vary their concentration in terms of the two raw materials, and you have the different measurement of the opacity. So here on that example, you do see that from the plot on the bottom left, those blue crosses actually allow you to visualize some dependency between the actual concentration of raw material 1 and its opacity, while in the case of the raw material 2, there is no actual correlation with the opacity. So the whole game for those machine learning techniques will be to define a function f that will actually map those concentration into the opacity world. So that's kind of simple up to the definition of f, and we'll see what we can do just after. Yet it relies on having some data, because if I don't have the data, no way I can actually learn anything from those. And it actually has some limitation as well. So here, it's quite easy to understand that if I'm taking a point between the blue crosses, I'll be easily able to interpolate because I have a logarithmic shape curve. And if I'm actually having a regression that captures that shape, it's going to be very easy to actually interpolate. Now, what happens if actually I go beyond the concentrations seen at training, or even if I go to new raw material that has not been seen for training, then it's likely that I won't be able to generalize, and I will do completely off results. Last thing, while it's not really theoretically limited to, those methods are really well suited for predictive tasks, and as I was mentioning before, we are also interested into the generative aspect to consider and sample new formulas. So that function f I was mentioning, it can actually be very simple or very complex. So you can actually go from almost no parameter in that function, which actually to some extent will lead back to the simulation case where all your prior knowledge is in the equation, which is very well constrained, possibly with a few parameters that you can train using a few data points. Up to fully unconstrained data. So here you will enter the realm of neural networks that would have almost no constraint on the shape of the function you are trying to learn. In between, you usually find the let's say machine learning algorithm where you have sort of a prior knowledge, not on the actual physics underlying, but rather on the shape, on the smoothness of that function. And depending on how many data points you have, you may want to either go from traditional few parameters up to fully unconstrained parameterization to actually either leverage your prior knowledge or your data. So here we do see that on the right there is that deep learning thing, which is a good segue to what we do see from a few years now with the generative AI. So behind generative AI, especially on text, what is done is the large language models. So here what is interesting is, unlike what I've been saying so far, where I was mentioning the capability of training function through your data, where you would control exactly what you would model, at the expense of needing to have those data, needing to do the training, needing to understand what you're doing. Here, the good traits or the good perk of the LLM is you don't need anything. Basically, most people are just using the LLM. They are asking whatever question, even if it's not been trained for that question. And the nice thing, or bad thing, depending on how you see it, is it actually gives you an answer that is, to some extent, valid. Now, don't forget that using an LLM is not actually training a model. And while it's easy to actually use it, the whole underlying part, the hidden part of the iceberg, as you see on the right, still remains, and you still have that complex neural network under the hood that requires some data, that requires the training and the creation of that model. So now, why do we see that LLM are not really well suited for the sake of cosmetic property prediction? So let's just make one stop on what they are and how they actually behave. So LLM are basically, to really make it very simple, they are actually predicting words one after the other. So if I'm taking one sentence in English, so in that case, how many legs has a cat, then the LLM will be trained to find the words that are the most likely to appear in a conversation between you and me. So in that case, we may have seen many documents during training that says, well, this is a question, therefore I will answer. So there will be a subject plus a verb. So the first word will be it has. Then we are talking about cats and legs and numbers. And in that case, usually the right numbers will be 4. So therefore, the LLM will be able to produce something like it has 4 legs. So this is actually working quite well for languages. Now, let's see how it's actually mapped for the sake of property prediction. So we'll see, and we'll take that example on the bottom right, where we don't ask the same question about cats and legs, because we don't really care for the sake of cosmetics. We'll replace that with cosmetics-oriented questions. So let's say we have 2 pigments, pigment A and B, and we want to see and to assess what would be the color of those pigments. So I will actually, again, make my sentence, so pigment A and pigment B, what's the color? And then the LLM is likely to answer red, which is likely to be true, okay, to be fair. Now, we have that wow effect because we didn't train that model for actually explicitly asking him to answer a color. He's actually doing the good job. But after that wow effect, there is, well, what does red mean? You know, it can be pale red, it can be really shiny red. We don't really know what was the surface. Was it a white background? What is a black background? What is the skin? What is a wall? So we don't really know what are the conditions of the measurement of that color. So if we actually make one step back on why we do have that behavior and why we can't expect to have much more than that behavior during the training phase, so that's what we see on the top right, what has been used to train the model was many sentences, maybe from one website, maybe from one document, maybe from one book, maybe from one emails that has been used for training. And maybe in those documents, you may have pigment A is red, pigment B is blue, pigment C is yellow. Now the thing is, those colors, while they are all color, they do not reflect to the same measurement protocol, unless explicitly stated in enough number of time, but which is usually not the case. So we just have the notion of color, but not the experimental setup. So there is no consistency of what we call a color, just the concept, the ambiguous concept of what color means in English, for instance. This is where the problem is coming from, because this is not consistent, so the protocol is not the same, and we don't even know that there is a protocol. While when we want to reformulate, when we want to have a formula that behave exactly the same as the previous one, then we want to have that exact same color. Imagine you go to your hairdresser to get a hair color dye. Then you wanted to have a black, and you go back home with something that would be more gray than black. Maybe you wouldn't be that happy. This is exactly what we want to achieve. So here I'm just stating that LLM directly are not suitable to actually predict properties of the formula. However, they are good at giving back property they already know, okay, if the protocol is well structured. And they're also good and very good at dealing with ambiguous data, especially in document. I won't talk about that today. You have plenty of things where you can actually use, in the context of cosmetics or in the context of whatever topic, how to use those LLM, using RAG, using knowledge graphs, all complex machinery around them. I will leave them aside and I will see how we can actually alter them to actually be able to give the answer we want in terms of characterization. So here I'm going to make one step back and one pause by looking at what we have in our case, so in L'Oreal. So L'Oreal is actually older than me by far, and it's been creating a formula almost forever, which means that we have plenty of data points of formula that used to be active in the past, are active now, will be active in some future. And as we matured our business, we started to characterize and more precisely those formula. So here we are in a position where we have many formula, we have many characterizations, so many data points, and we can actually do what is being done at the scale of large language model, but on formulation data. Which lead me to the creation of a formulation model. So here, formulation foundation model, it's basically using the same techniques, the same technology as what we do see with ChatGPT, Gemini, and all that stuff, so transformer-based approaches. For instance, not limited to, but that's one good example. And we will try to actually take the benefits of what is working from the LLM, which is, in a nutshell, you have the ability to capture the correlation between all the words in a sentence, okay? So that's why it's working so well. You have no kind of limitation in terms of context of windows of what you're seeing. You just get the correlation with all the elements within your sentence or your text used as an input. So here we can actually do the same, but instead of using plain English, which is ambiguous by design, using our own chemistry language, our own formulation language, where we describe what is a formula, what is a property, what red mean, what is the protocol, the measurement protocol associated with a given color. That may differ depending on the protocol being used, and get to something that is an ambiguous language model to something that is really precise, where we know exactly what we want to do, backed up by the data we are using. So that's exactly what we are doing right now, and that's a collaboration with IBM, IBM Research Centers, where we are developing that first foundation model within the company. So now, in terms of capability, with that, we will be able, as the example says, to predict the performances on a specific part of the formula, but also, because LLMs are by design generative models, we would be able also to create new formula and to get proposals of formula achieving a given targeted set of parameters. So to wrap up about that small presentation. So we see that AI is not just a single thing, and depending on what you want to do, depending on the data regime you're in and what you want to achieve, you may actually either get back to old-fashioned way that are really good stuff to actually do accurate simulation, up to traditional machine learning, up to modern machine learning, and more likely you may actually end up mixing all those stuff, especially with the case of LLM, that may actually play many roles by not just replacing AI as a whole, but orchestrating and leveraging different pieces of AI. And that's where I'm going to stop for today, and I'll be happy to answer any question of yours.
Alors, so thank you very much. We can. Thank you, Giovanni Palma. Have you got some question for him now? Yes, I come to you with the microphone.
Thank you for these explanations. It was very clear. I wanted to understand where are you in terms of execution concretely with the formulation teams? Are they using your IA or is still under development?
So it's not a binary question. So things are being built for years now, actually way before than my arrival in the company. So we are using part of those types of algorithms, so mechanistic for sure, regular machine learning for sure as well, and LLM, obviously, like any company, since the last 2 or 3 years, we are using them as well. And the foundation model, that's something that is being developed, that is already existing as of today, that gets on its way to be refined, rolled out internally.
Okay, thank you. Some questions here.
Thank you very much. Thank you for the presentation. I have one question. How you check or verify the robustness of your given formula by this AI?
So in the end, the only judge is the actual measurement in the lab. Okay, so whatever we do, we assess that with actual measurement. So it can be formula non-used for training, for instance, that we already know, or even proactively, it could be formula that we'll create, because as I was saying in introduction, our job is to actually create formula. So there are many, many formula being created each day, each week, each month, each year. And using that, we can validate, refine, kind of similar to some talk where active learning was mentioned, being able to correct the error of a model and refine and validate it by some means.
Okay, thank you. No more question now? Yes, Fadi.
Thank you, Giovanni. Very fascinating talk. And you mentioned that the advantage of large language model is that if you have a sort of a plain English or a literature data, then it works quite well. And you highlighted the fact with formulation and specificity. So I wonder whether in L'Oreal it's you use pre-existing, pre-trained transformers, or you try to capture, I don't know if it's the right word, the brain of the artisan, because you mentioned also about the gut of the person formulating that art. Do you train your own LLMs as well based on your set of knowledge that has been built over the years?
Okay, so there is no real sense in actually training your own language model on sentences. Barely you can motivate fine-tuning one, but it's really hard to actually justify the huge amount of money in respect of having one GPT coming every 2 or 3 months. Okay, I stopped personally counting them as they are too numerous. So I'm just taking whatever is on the shelf when using them. So it's kind of a lost battle by the beginning if it's not your core business of using and training an LLM. That being said, you can actually design around those LLM to actually fit your needs. Could go by fine-tuning, for instance. Could go by defining your own data pipeline, your own way of constructing, structuring, or not structuring the data. And that depends on what you want to do, what is the piece of the business you are interested in. And you can do either off-the-shelf stuff or a bit bespoke stuff. Yet, actual training, you resolve that to something that will never be done by any GAFAM, like I was mentioning that foundation model for formulation.
Excellent. Thank you very much.
Welcome.
C'est bon? Thank you very much. Thank you, Giovanni Palma, for the example, the illustration at L'Oréal. Thank you again. Merci à tous. Merci. So, on va avancer vers la table ronde. On va avoir un petit aménagement de lien vers le nouveau stream. Et je vais demander à Chrysoula Tassou de me rejoindre. Effectivement, we are going to have a high-level roundtable discussion with Chrysoula Tassou. Vous pouvez me rejoindre. Nous allons ensuite appeler les intervenants. Dans quelques instants, on va vous installer tranquillement. C'est Chrysoula qui va animer cette merveilleuse table ronde devoted to how AI is transforming professional practices in process formulation and development. Voilà, exactement. Donc, rejoignez-moi, je vous laisse la